Hi guys, welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on heat transfer by free convection, and we're going to be modeling this as a 2D geometry. So this example describes a fluid flow problem with heat transfer in the fluid. So we've got heating tubes going in the horizontal direction, fluid flowing vertically. So it could be a liquid or a gas. I don't know yet. Fluid is any substance that deforms continuously with pressure, or I think more specifically shear stress. So we've got heat transfer in the fluid by convection. So you can have heat transfer by conduction, convection, or radiation. This is modeling free convection, a specific type of convection. Okay, so our model definition is going to be based on the consideration that there's no variation in the third dimension, so it can be extrapolated from the solution of a related two-dimensional case. So basically we're simplifying the model by neglecting any end effects from the walls of the vessel and assuming the solution is constant in the direction of the heating tubes. So in the horizontal plane, we're assuming that's a good snapshot of the 3D problem, but a much simpler solution in the 2D domain. Okay, so using symmetry, as shown in figure 2 here of the tutorial, to reduce computation time and complexity, the model describes one section of the array of heating tubes indicated by the dashed lines. Here, the next step is finding symmetries. In this case, use symmetry planes. Using symmetry planes, it suffices to model the thin domain indicated in figure 2. This is a multiphysics model because it involves fluid dynamics coupled with heat transfer. Because, of course, we've got fluid moving, so that has mass, and the mass moving has some thermal energy that it's carrying with it, so it's transferring heat by convection. The pressure P and velocity fields U and V are the solution of the Navier-Stokes equations, while the temperature T is solved through the heat equation. These variables are all related through bidirectional multiphysics couplings. Right, so that's just a little background on the governing equation, Navier-Stokes. And if you've ever solved the Navier-Stokes equation by hand, it's very painful. So that is why computational solvers like COMSOL or other CFD softwares are very helpful. So for our results, the analysis of the coupled thermal fluid model provides the velocity field, pressure distribution, and temperature distribution in the fluid. Figure 3 shows a plot of the velocity field and temperature. So this is what we're going to create in this tutorial. So this is, let's see, on the x-axis we've got meters and meters in y direction, and then a color gradient showing the temperature in Kelvin with arrows on the surface plot. Using integration to find the mean temperature at the outlet shows that the temperature increases roughly by 1 Kelvin from the inlet to the outlet. And in this case, they're saying we're coupling the laminar flow and the heat transfer in fluids for both x and y directions. The buoyancy force lifting the fluid is entered in the compressible Navier-Stokes equations via a force term F, depending on temperature through the density. At the same time, the heat equation accounts for convective heat transfer. Alright, so we've got two things to consider here, the buoyancy force and the convective heat transfer equation. Use the non-isothermal flow multiphysics node to automatically use the temperature field computed in heat transfer in fluids and laminar flow, and the velocity and pressure from laminar flow into heat transfer in fluids. Alright, so there's the background, and we're going to start with a 2D model from the model wizard. Let's shrink this down in the screen. Alright, that looks good enough. And then for physics, we're going to select fluid flow. And just make this slightly wider there. I don't know how to get rid of this thing. That's good enough. Okay. Fluid flow, single phase flow, laminar flow. So under fluid flow, expand single phase flow and laminar. So as you can see, that's the only option here, SPF, and you've got some background over here. The laminar flow interface is used to compute the velocity and pressure fields for the flow of a single phase fluid. So that's what our SPF stands for, single phase fluid, and the laminar flow regime, as opposed to turbulent. And I believe if you want to model turbulent flow, you have to purchase an additional module, which I don't have. A flow will remain laminar as long as the Reynolds number is below a certain critical value. At higher Reynolds numbers, disturbances have a tendency to grow and cause transition to turbulence. This critical Reynolds number depends on the model, but a classical example is pipe flow, where the critical Reynolds number is known to be approximately 2000. The equation solved by the laminar flow interface at Navier-Stokes equations for conservation of momentum and the continuity equation for conservation of mass. Alright, so let's add this physics. So we also want to select heat transfer and heat transfer in fluids. Add. And now study. Because we've got two physics to couple here. In the select study, select general studies stationary and done. So I'm going to go ahead and save this. You can't save it until, you can't save the multiphysics file until you select your model type. So I'm going to save this as free convection. Let's see. Free convection is good enough. Alright, in the model builder window under global definitions, click parameters 1. And then in the table, we're going to enter all of these parameters. So v underscore n is our variable for inlet velocity, 5 millimeters per second. T underscore n is 20 degrees Celsius. It's our inlet temperature. And T underscore heat is 50 degrees Celsius. We have to put the units in brackets like that because, as you can see, the standard SI unit is Kelvin, which is what COMSOL expects if you don't specify another unit. Right, and lastly, the heater temperature is T heat. So now we're moving on to geometry. In the geometry toolbar, click rectangle. In the settings window for rectangle, locate size and shape, and in the width, we're going to type 0.005 and the height 0.04. So what we're saying is a 5 millimeter by 40 millimeter rectangle. So you could put that in as 5 brackets millimeters, just as easy to put a small decimal, the standard units of meters. And now we're going to add a circle of radius 0.0025 meters and position off-centered from the origin at y equals 0.015. Okay, so there's our circle. And now we're going to create a difference by going to Booleans and Partitions, difference, rectangle minus circle. So it looks like, okay, so these are the heating tubes, these circles, and this is basically half of a heating tube, a section of the array of heating tubes shown in this picture. So we're basically just isolating one of those tubes and showing the flow around it because we're assuming that it's the same across the array. Okay, define a non-local coupling for computing average values over the outlet. In the definitions toolbar, click non-local couplings. So I'm clicking on definitions up here. Non-local couplings is this link icon, and choose average. In the settings window for average, locate the source selection section and choose boundary from the geometric entity level. So we're changing it from domain to boundary since we've got a 2D problem with an inlet and an outlet represented by lines here instead of domains. Select boundary for only. Right, and then the operator named text field, type average out. AVE out. Using this coupling, define a variable delta T for the temperature rise from inlet to outlet. Right, so we're going to create a variable. In the definitions toolbar, click local variables. So this A icon, first one on the left. And we're defining a new variable delta T with expression average out argument T minus T underscore N temperature rise. So let's see, T underscore N we already defined in the global definitions parameters. So it's saying it didn't recognize it. Oh, I spelled it differently. That's why. Okay, so it should be AVG. I had AVE. Alright, so now if we go back, this shouldn't be yellow. Yep, good. Okay, so that's one good double check for yourself. If you ever see something in yellow, it either means you haven't defined it, or if you know you have defined it, either the function or a variable it's calling, then there's probably a typo somewhere. Alright, so we're good there. Now we're going to go to add a material. In the home toolbar, click add material. And we're going to look for water. So this is from the built-in materials. Okay, so you can either double click or add to component and then exit. And then add a non-isothermal flow multiphysics node to set up the velocity and heat transfer and to account for multiphysics stabilization. So we're moving on to the multiphysics definitions. In the physics toolbar, click Multiphysics Couplings. So up here, I'm going to click on the physics toolbar, click Multiphysics Couplings, and our only option here for domain is non-isothermal flow. And under laminar flow, since the water density is temperature dependent, the flow is set to weakly compressible. All right, because as water heats up, it does become very, very, very slightly more dense. Right, yeah, it's backwards for most fluids, but for water, it becomes less dense as it cools, as it freezes. Okay, so in the model builder window under component 1, click laminar flow here, and in the settings window, locate the physical model section. And we're changing this from incompressible flow to weakly compressible flow. Your other option here is compressible flow for Mach less than 0.3. So we're choosing weakly compressible since we do have a delta temperature across the domain. And in Symmetry, Physics toolbar, we're going to choose Symmetry. So Physics, Boundaries, Symmetry. So we're creating a symmetry condition for boundaries 1, 3, and 5. So this is the vertical bounds of our two-dimensional model of flow. So you have fluid flowing upward on the left and the right. So it's symmetric in 2 dimensions because we have to keep in mind we're modeling a 3D problem that is symmetric on these axes. Inlet 1. In the Physics toolbar, click Boundaries and choose Inlet. So now we're creating an inlet boundary condition. Select boundary 2 only. So here's our inlet. Water comes in from the bottom and flows upward over the heating element here. In the settings for inlet, locate the velocity section, and in the U not text field, type VN. So this was the global definition parameter we defined earlier, velocity N in meters per second. And finally, for our outlet condition, we're going to select boundaries, outlet, and define the outlet condition for boundary 4. Okay, so we've got an inlet condition, an inlet boundary condition, outlet boundary condition, and 2 symmetry conditions. So we've got a governing equation that should have an order of 4. Why you need these many boundary conditions, it's helpful to look at your governing equation. So you can go into the heat transfer and find that equation, and you can go into laminar flow and expand that equation to find the governing equation that COMSOL will actually be solving for. So we've got rho of u times del u equals del negative pi plus k plus force F, and del rho u equals 0. Alright, so the general form of Navier-Stokes is, the most general form of the Navier-Stokes equation, convective form, is here. Here we're solving in 2 dimensions, the x and y dimension. So the x component will be expressed like this, with partial derivative of the x component of velocity with respect to time, with respect to the x direction, and with respect to y. And then the y component is the same here, and then you multiply it times u. So you multiply through the x component by the partial with respect to x, the y component by the partial derivative with respect to y for both the x and y expressions of the Navier-Stokes equation. And then your total solution would combine the x direction and the y direction solution. So that's the left-hand side of the equation. And on the right-hand side of the equation, you've got del negative pi plus k. So let's see, what is I and k here? 1 plus F, and F here is your buoyant force, so that's the plus rho times gx for the x direction and plus rho times gy for the y direction. So that's g is gravity, and here we've got a buoyant force, so it's going to be overcoming gravity. And then in parentheses here, so here's your p term, the negative p, negative partial partial derivative of p with respect to x for the x component and with respect to y for the y component, plus the second derivative of the x component of velocity with respect to x and y, and for the y solution, second derivative of the y component of velocity with respect to x and y. So when we look at the order of the solution, we have to look at the bottom part of the partial differential equation. So we've got second order here. So we need two conditions for the y direction, two conditions for the x direction. This one's only first order, so those are, we don't need any additional conditions for those, but we do have a time condition here. So that means we need one initial condition. So that means we need 1, 2, 3, 4 boundary conditions physically, and then one initial condition temporally. We've got a fifth order IVP, initial value problem. Okay, so here's our two symmetry conditions. So we've got a 2 for the y for the symmetry, 2 for the x, inlet and outlet. Now where is our initial value? Well, we haven't gotten there yet, but that's going to be our fifth one. So we've got 1, 2, 3, 4, 5. And you should always be able to do that with your problem by breaking down the order of your partial differential equation to figure out how many initial or boundary value, boundary condition values you need to set. So we're going to initial values. It's already here, so we don't have to add that condition like we did for the symmetry and inlet and outlet. In the settings, find initial values, and in the P text field, type SPF, single, single phase fluid dot row ref, so reference density times gravitational constant times 0.04 units or meters minus y. Alright, so this is the expression we're defining to solve for the pressure profile, the initial value for pressure. And then volume force 1, in the physics toolbar, click domains and choose volume force. So in domains, you can choose fluid properties, volume force, or initial values. So we're going for volume force, and under F, the x component stays 0, the y component will be negative gravitational constant times SPF dot rho. Yeah, the buoyancy force lifting the fluid is entered in the compressible Navier-Stokes equation via a force term F, depending on temperature through the density. Okay, so that's why we've defined it like this, because we don't have a constant buoyant force. It's going to be dependent as the temperature is heated past this heating element. Rho is defined by the material, the built-in material water, and that has its own function. In the background, it'll figure out what rho is for a given temperature, and that will go into the solution. So the density isn't a constant, it's an argument, or it's a function of temperature. Right, so moving on. Okay, so show advanced physics option as follows and enable pseudo time stepping for the laminar flow equation for better convergence. Click the show more options in the model builder toolbar. So this little icon up here, it looks like an eyeball with a scroll over it. You can say show more options, and then we're going to select advanced physics options. So we're going to click this to enable it. Okay. In the settings window for laminar flow, click to expand advanced settings and find the pseudo time stepping subsection. From the used pseudo time stepping for stationary equation form list, choose on. So instead of automatic from physics, we are selecting on to use pseudo time stepping. And why we are doing that, and it looks like this is some documentation from the COMSOL Multiphysics reference manual for pseudo time stepping for laminar flow modules. This equation, which was the equation of theory, requires a starting size close enough to the final solution. No such guess by hand, the fully transit problem can solve instead. This is a rather costly version of computational time, so the effort is to add a fictitious time derivative to the equation. U minus no jack u will result in t bar, where t is a pseudo time step. Since u minus no jack u is always 0, this term does not affect the final solution. It is however effectively symmetric from some nonlinear iteration to a step time instead of the size of t bar and solver. I don't know how we would know, just modeling this from scratch, that we need to do that. Maybe you figure it out when you try to compute it, and it takes an hour and a half. So this is new to me, the pseudo time stepping, but that's a useful hack, it looks like, for laminar flow to save on computational costs. All right, so we turn that on. Now we're going to define our boundary conditions and initial value for heat transfer and fluid module. In the model builder window, select the heat transfer and fluids, and in physics, we're going to select boundaries and add temperature. Boundary 2 is the inlet, so we'll select that. And in the settings for temperature, we're going to put T underscore N that we already defined, temperature N. And for the outlet, we're going to add another boundary for temperature and select 6 and 7. Let's see. So the curved part of the heating element is going to have a temperature condition of T heat. T underscore heat for the heating element temperature. And finally, outflow. So we're going to click on boundaries. Where's outflow? Here we go, flow conditions. Okay, and we're going to select the outlet boundary 4 up here. And now we're going to do a symmetry condition, boundary, symmetry 1, 3, and 5. So the left and right of our flow domain. And finally, our initial value. So we're going to go to temperature and define Tn. So you'll notice Tn, which we defined under the global definitions at the beginning, inlet temperature is both a initial value condition and the temperature 1 condition. Alright, next is defining the mesh. So under component 1, right click mesh and build all. So we're not changing this at all. We're going to go with the default values, which is a normal element size physics controlled mesh. And there you can see the mesh that appears. And now we're ready to compute study. So in the home toolbar, click compute. So you can go to study 1 and hit compute here. Alright, and 11 seconds later, it's done with the surface plot showing the velocity magnitude from 0 to 16 on a scale of times 10 to the negative 3 meters per second. So we've got about 6 millimeters per second here, or let's see, the inlet condition was 5 millimeters per second, and then it ends up going faster on the left hand side at the outlet with a maximum of about 16 millimeters per second, and then almost stagnant on the right hand side. So that's interesting. And now we're going to add some arrows to our surface plot. So the default plots visualize the velocity. Yeah, I'm recording. The velocity, pressure, and temperature fields. To reproduce the plots in Figure 3, modify the temperature plot. Arrow surface 1. So in Model Builder window, we're going to right-click on temperature HT. So go to temperature, right-click, and click arrow surface. In the settings window, locate the arrow positioning here, and in the X grid points subsection, we're going to put 10 points instead of 15. And we're not changing the Y grid points. Locate the coloring and style section. From the color list, choose white. So we're making white arrows and plot. So there's our arrows. You can see if you zoom in. Let's see, are they thicker if they have magnitude? No, arrow length is proportional. So it looks like the length of the arrow, because up here we've got a velocity field that is much faster on the left hand side and nearly, what am I doing here? Zoom out and then zoom in, there's what's centered. Okay, and nearly stagnant on the right hand side. So you've got a tiny arrow that's in fact moving backwards. That's interesting. So you've got a little bit of a backflow here, but very strong outlet flow on the left side. Okay, click the Zoom Extents button, and finally evaluate the temperature rise. Global Evaluation 1. In the Results toolbar, click, what is that? Icon for Global Evaluation. So we're clicking on Results toolbar, and there should be an icon for Global Evaluation. All right, and click Replace Expression. So this red and green arrow, we're going to replace the expression with Component 1, definitions, variables, and the expression for delta T minus temperature rise in Kelvin. So double clicking on that, it populates the field in the expression section, and we can hit Evaluate. Go to table window, the value should be close to 1 Kelvin. So now under here, we've got the table section, table 1. Oh, it appears in so in the bottom right hand section, if you have the default window setup, you've got messages, progress log, and then table. So right here, it shows you the temperature rise in Kelvin is 1.078 Kelvin. So that's it. You've got a velocity surface plot, a pressure surface plot. I don't know how helpful that is. You can also, or contour plot, sorry, not a surface plot. Velocity is a surface plot, pressure is a contour plot, and temperature is a surface plot. And then you've also got isothermal contours for the heat profile, if that's interesting to you. And then of course you can export, edit your coloring and style for any of these surface or contour plots. And yeah, so that was fun. I hope you guys enjoyed it. This was a tutorial on heat convection or heat transfer by free convection. Alright, so that was today's tutorial on modeling free convection in a two-dimensional model. So I hope you enjoyed it, and please subscribe for more COMSOL tutorials, and be sure to like and comment. Thanks, and I'll see you next time.